Hey everyone, it's Kyle Shevlin here, coming to you from what's actually a pretty beautiful day here in Portland, Oregon. Fall's about to start. There's a little bit of cloud, a little bit of mist, but the sun has peeked through right now. It's making me pretty happy, and I hope wherever you happen to be in the world, I hope you're having a wonderful day as well. I want to give big thanks to Christian for putting together Byteconf. I'm really excited about the opportunity to speak with all of you. And I really hope this idea could take off and proliferate. I think it's a great opportunity for people everywhere they are to have a chance to listen to some good speakers. I'm hoping I'm one of them, but also just participate in that conference feeling without necessarily having to spend all that money. I think it's a great idea. Thank you, Christian, for putting that together. That being said, I have a few quick warnings I want to give all of you. For the last 5 or 6 days, I've unfortunately been kind of sick. I've had my nose has been stuffy, my throat's been scratchy, so you might hear it in my voice as I'm going. I'm going to do my best not to hack and cough up a lung while I'm talking. Lucky for you, you can't get sick from me, right? Like, there's no way to pass this contagion, so you're the lucky ones, at least, I think. That also being said, I will be in the chat. That's right. I'm recording this on Monday. You're watching it on Friday, and I'll be in the chat to answer any questions that you might have. In other words, my future self will be there to correct and clarify my past self, and to you, you'll experience both as present self. That's it's not a bit of a mind warp at all. No, no. Also, I'm going to try not to be so casual. I'm here in my Twitch setup. Sometimes I stream on Twitch, and I like to have a good time and chat with my my audience members. You're not here to chat with like as I'm recording it, but you're there while it's going on. But I'm going to try my best, stay focused for y'all, and get through this. So with all that being said, I'm going to change the coding scene. I'm going to change the coding scene like I have a scene on OBS, and you'll see more of the screen and less of my face. All right, assuming everything went right, my face should be much smaller down in the corner and you should be able to see most of my screen. My talk, the one that I'm sharing with y'all, is called Learning Backwards, Learning Computer Science Through the Lens of React. And before I dive in, I thought I would share a little bit about me just in case you don't know much about me. I'm a JavaScript engineer. I'm currently fun employed. That's right. Emphasis on the fun. I'm trying to take some time off to relax a little bit and figure out what I want to do next. If you have any questions about that or want to work with me in the future, go ahead and send me a DM on Twitter or anything like that. But trying to enjoy it the best I can. I'm also the host of the Second Career Devs podcast. You may have heard of it. If not, no big deal. What I do is I find people who have made career changes from one career into web development or software engineering, and then I try and I interview them to find the lessons that they could have only learned from making that kind of career switch. What alternative knowledge and skill sets do they bring to the table, and how do they use that in their work? It's awesome. It's got a decent growing community, and I'd love for you to join it. I'm also an Egghead.io instructor. You can follow the links here. I will post the slide up so that I'll post the deck up so that you can follow along and do the links and that kind of thing. Hopefully I remember to put the link in the chat so you can do that. And then, as I already mentioned, I'm an occasional Twitch streamer. I love teaching and training people. I love helping people learn how to make cool things with these technologies. I love JavaScript. I love React. I just think it's a wonderful time to be in this career, and it's just a really good feeling to be able to help people grow and build up their confidence in making cool things. And so hopefully that's what this talk will be for you. It'll be a way of introducing you to some computer science concepts that you may or may not already know, and give you the confidence that if you haven't learned computer science before, that you can start to dive into this this arena of thought and knowledge and be able to use it in your work. Now, I'm pretty affirmative about this, but you might be asking, do I need to know computer science? Do I need to learn it? Well, to be frank, the answer to that is kind of I don't know. Right? Computer science and having the knowledge of it isn't a prerequisite for getting started in this career. I certainly didn't have it. As I alluded to earlier, I'm a second career dev myself. I didn't have computer science knowledge when I got started, but there might come a but there might come a time in your career where starting to gain this kind of knowledge could be really useful. Let me give you an anecdote, and it'll kind of serve as the inspiration for why I wanted to give this talk. So, as I mentioned, I changed careers. Before I was a developer, I was a pastor. I worked for several churches and I did ministry for quite a while, and I have a master's of theology. But while I was earning that degree, I kind of caught a bit of a bug and I started to teach myself how to code. I think a lot of you can relate to that. I spent my time on lots of platforms that gave you training. Mine in particular was Code Academy was the one I used a lot, but I also just use lots and lots of tutorials, and I just kept teaching myself again and again. And you learn a lot, and you figure out how to build a lot, but you don't actually necessarily have a foundation underneath what you're learning. Like you're learning languages, maybe libraries, but maybe not what's underneath them and what girds them up and gives them the power and the capabilities that they have. So I was able to get my first job with just knowing HTML, CSS, started learning Sass at the time I got the job, and some jQuery. That was more than enough for this agency here in town that I started working for, and I got really good at it. I got really good at making custom, responsive front-end architectures. I wrote some Sass libraries and that kind of thing. I got really good at it, and eventually I plateaued, right? I think most of us, for those of you who are in your first job, at some point you're probably going to plateau and you're going to reach a point where the best way, or maybe the only way for you to move up and do the next thing in your life is to switch jobs and find something more challenging to do. And that's what I set out to do. I took a new job. I switched to JavaScript. I'm so thankful that I did. It became the new hotness like I expected. And man, it's a wonderful time to be a JavaScript developer. There's just so much you can do with the language, and the opportunities seem almost endless. But again, I hit a plateau. And this is kind of where this story comes in. I hit a plateau after doing that job for a while where I had learned JavaScript pretty well, but I still hadn't learned any of the real computer science behind it. I started to interview at some bigger companies. I can remember quite a few of them, and I had to do some of those dreaded whiteboard algorithm interviews. And I got my butt absolutely kicked because I didn't have this background knowledge. I didn't have this foundation of how to take an interview problem without code and find a way to make an algorithm and to optimize it and understand what was going on. The truth is, like, I was trying to make the transition from developer to engineer, but I didn't have the foundational knowledge I really probably needed to be an engineer. And so I had to go out and I had to start learning it, and I learned it on my own. And later on in the talk, I will share a lot of the resources that I used to learn it, and I wouldn't be able to do what I do without some of them. And now that I've learned a bit of it, it makes me really excited to continue to learn more and more. It's inspiring, and I hope I can do the same for you. So at the end of this, I really think the answer comes probably at some point in your career. Developing a good foundation of some computer science can go a long way to augmenting the knowledge that you use in your day-to-day work. Your day-to-day work, you might be like me. You might be a UI dev primarily, where you're putting things on a page and you're showing lists and that kind of thing. But at some point, in order to maybe make the libraries you have in your head or do other things, optimize your code and your application, having some of this foundational knowledge, whether you learn it through, say, the hard knocks of just doing it, or you learn it by someone like me teaching you, or a book or a tutorial, it doesn't really matter. What matters is that you develop this knowledge base that allows you to make decisions and understand the trade-offs you're making in your code more clearly, right? I think another benefit to learning some CS is it helps you pass technical interviews more often. You won't get stumped by problems quite as often. You won't feel as nervous when someone gives you a strange question. You'll be able to ask the right questions of them and get the answers you need and be able to develop an algorithm to solve the problem. And I think that's awesome. I do think, we should admit it maybe kind of sucks that we have to do whiteboarding interviews, and there's these rituals of interview processes that we still go through. But that being said, you can't fix it just by yelling at it to be different. I think one of the better ways is maybe a few of us with alternative paths and alternative knowledge sets. If we can gain some of the knowledge we need, we can get into those positions, we can get those jobs, and we can start to change the culture from the inside. We can point out, like, just as a few big companies this week, right? They removed the education requirements from their job postings, right? I think that's going to go a long way to proving to the world that there's lots of smart people who can do an excellent job at all these jobs, regardless of where their background is, so long as they have the knowledge that they need to get the job done. And I think computer science can really help you have that kind of knowledge and confidence. Lastly, being able to get a better job, it might mean having a better life. I mean, who doesn't like maybe a little bit more money or a little more freedom or a little more responsibility in the right ways, in the ways that fit them and suit them best? I can't guarantee that a better job leads to a better life. Sometimes what seems like a good job isn't so great. Sometimes, life is just challenging, and it doesn't matter how good our job is. That's the challenge of life itself. I can't fix that. I certainly can't do it in this talk, but some computer science can go a long way to helping you develop the knowledge set that you need to be able to get those jobs that might be life-changing for you. So that being said, I want to get into some foundational knowledge that we need in order to understand the three things that I'm going to talk about today in relation to React. The three things I'm going to talk about are, I'm going to talk about data normalization, I'm going to talk about memoization, and I'm going to talk about trees, the data structure, right? I'm going to talk about these three things and how they relate to React and our code. But in order to do that, I need to give you a little bit of a brief understanding of something called Big O notation, so that we can use that foundation to talk and build upon the other parts of this talk. So Big O notation, as I like to jokingly call it, and you can see it here in the title, is how bad can my code be? If you've never taken a computer science course, which I'm hoping a bunch of you haven't, if you have taken computer science, I hope this gives you like the language and a primer for talking to people who don't have that background, to give them that information if they want it. So what is Big O notation? It's a standard way of describing the worst case scenario, the worst case performance of an algorithm in regards to time or space, right? Worst case scenario of how an algorithm works. Now, that being said, you might be wondering, what is an algorithm? That's a good question. I should probably have hit that first. I know I've said it about half a dozen times already, but just to be clear, an algorithm is a procedure for solving a problem. That's it. It's not really scary at all. It just goes from the beginning to the end. It's the step-by-step way we solve a problem. So whenever I use the phrase algorithm, I want you to think procedure. I want you to think step-by-step instructions. Got it? All right. So Big O notation, as I said before, I'll go back a slide. Big O notation is a way of describing the worst case performance of an algorithm. Why do we care about the worst case? Well, there are ways that we measure the best case and even the average case, but the worst case is the one you'll probably be asked the most in an interview question, and it's also how we can optimize our algorithms the best. If we can solve for the worst case scenario, we know every scenario below that's going to perform better. So we've improved the performance of our application and our code and our programs by making our worst case scenarios the best they can possibly be. So we just need to come up with a way of talking about how bad our code can run. Now, the first one you've probably ever run into, if you've ever seen this, if you've ever seen it at all. If you haven't seen it all, I'm just going to walk through some of them. The first one you'll see is O of 1. What this means is that our algorithm runs in constant time. Now, when I say that, constant time can refer to the time it takes for an algorithm to run constantly. If I say constant space, it means it uses the same amount of space regardless of how big the data set is. Same thing with time. No, regardless of how big the data set gets, it runs the same way. I have some examples on the screen. We're going to work through them really quick. You can see first on the first line, I have the function foo. That all it does is return the string foo. There's no computation there. This is a referentially transparent function. All it does is we call foo, and as fast as the program can run, it's going to give me foo back. This is an asynchronous. We'll think of this as synchronous right now, right? That's a constant runtime. As fast as the runtime can go, we get that back. The same thing happens when we have our first function. Our first function takes an array and returns the first item of that array. The reason this is constant time is because we're getting an item out of the array by index. We're going to talk about what it means to get an item out of the array by something other than the index. But if we know the index in our array, we get a constant time lookup. We get that right away. We also have a function here, prop. Prop just takes a key, it's a string and an object, and I'm going to get the value off that key and the object. Hash tables, objects, dictionaries, enums, all these very similar data structures you might have heard of, all of these have O1 lookup time. And the reason being that the objects stored in memory, like we can just go to that location of the key. We don't have to do any computation. We hit the location, and as fast as the system can go, I know I've said that a bunch, but this is what you want to get in your head. As fast as the system can go, it gives me that value. There probably are some really staunch people out there, maybe not listening to this, who will be like, blah, 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 and give you a bunch of hoobity goobity gook. And that's a technical term about like how objects aren't properly implemented hash tables and stuff like that. Don't let them get to you. As you're learning this, just think of it this way. An object gives me a constant time lookup from a key to a value. All right? The next one we want to get into, this one you'll run into quite a bit. This is called big O of n. So n represents the length of our list, array, or collection that we're passing into our algorithm, and typically means that we have to hit as many computations as there are items in that collection. This is what happens whenever we have loops in our program. For example, if we're seeing or if we're using for each, map, find, reduce, these prototype methods on an array, those are running in on time. We can't exit them early, and they have to go over every single item in the array. It's not such a big deal if your arrays are pretty small, but if your arrays are millions and millions of items, you do want to be aware of the runtime of that algorithm that you're doing. If you have 1 million items, you have to run 1 million computations, and that could take some time. And that's something to be considerate of as you're writing your programs. The next one is on squared, and we can get to like on cubed, on quadded, I guess. I'm not sure what the word is there. What this is essentially nested loops inside of an algorithm. And I wrote a little bit of code here. You really want to watch out for nested loops in your application because they can take a small data set and very quickly make it many, many exponentially more computations to do at runtime. And that can really bog down system resources, especially if you have a large data set. So you have to be careful about this. And we'll talk about, when we talk about data normalization, how we can make a data structure so that we don't necessarily need to do these many loops, or we can make some trade-offs in order to speed up some computations. But let's look at this. We have an array. It's an array of numbers, 1, 2, 3, 4, and 5. And I have a function 2D array. We're going to make a two-dimensional array out of that first array. And what we do is I'm mapping over the first set of numbers, but each time I map over one. So for example, the first n you see there is a 1, right? For each one, that 1, I'm going to go over all 5 numbers again. So essentially, I'm multiplying each number across the array. And then you can see if I console log it out, what do I get? I get a two-dimensional array. I get the first lines multiplied by 1, second lines multiplied by 2, third by 3, fourth by 4, fifth by 5, right? We've taken 5 items. And now we have 25 computations, right? That's an order of magnitude bigger in this case, right? It's an exponentiation, right? Imagine we had 100, right? Or thousands or millions. We'd end up with tens, hundreds, billions of computations if our list is too long. So we have to be careful about letting that happen. I was going to explain this next one, O2 to the end. It's a little challenging for me to explain, to be perfectly honest. I did a take of this talk already, and I just didn't feel super confident about it. I can tell you what this can commonly happen in is in recursive functions, though the next one we're going to talk about also happens in recursive functions. It's essentially the idea that each time we add an item, we're making another exponent of 2. So 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and you can see how it quickly ramps up. We want to be a little bit careful about runtimes in this regard, and I encourage you to go look up some more information on the topic in order to learn it and really grok it. But this one, O log of n, and it's the last one I'm going to do. I know this can be really boring, but I do want to lay these foundations before we move on. O log of n actually happens quite a bit often, and we can make that a pretty acceptable. Big O notation to have in some of our algorithms. Like we might not be able to constant time, we might not be able to do just the list, but log of n isn't so bad. Logarithms, if you look them up and you maybe look them up on Wikipedia or something, essentially a logarithm works on orders of magnitude. We go 1, 10, 100, 1,000, 10,000, etc. Or we decrease in that same amount. What that means for you and me as people just learning some computer science and getting into this, what it means to us is an algorithm doesn't scale linearly with each item we add. O of n is a linear time, right? For example, if I double n, right, it's twice as long. With logarithmic time, I can double it and it won't be quite double the time. I'm going to have a resource at the end of this called the Big O Cheat Sheet. I encourage you to go look it up. It does a really wonderful job of showing you these different Big O notations, how they relate to each other on a graph, and it even gives you data structures and how they're things like find, search, input, replace, all these methods that you would expect on them. It gives you a good idea of their runtimes and will help you gather these. A typical case for log n would be doing like binary search on trees, which we're going to get to. In this case, a tree is a data structure that rather than having one long list, and I'll get into the real definition later, we can hold a lot of items in such a way that I don't have to go through the whole list to find things. I'm able to partition off portions of it and reduce and divide and conquer the data set as I'm trying to find or do things in operation. So that's a really quick primer on Big O notation. I've got a few tips I want you to remember when it comes to Big O notation. The first one is we typically drop coefficients. I didn't get a chance to say this, but specifically with like Big O of n, for example, if I run loops in series, not nested, but again, in parallel with each other, essentially, right? For example, let's say I have an array and I call map, and then I do another map for some reason, then a reduce. That's 3 loops. That would be a runtime of 3n, right? Because we're going through it 3 times. We're not so worried about coefficients. So when you're figuring this out, when you're doing an interview or something like that, we drop the coefficient, which in this case is 3. Why? Because 1 million isn't really all that different than, say, 3 million. It's really not that much in terms of computation. We're much more worried about exponents and orders of magnitude getting increased. So that has some ramifications for our code I'll get into in the next slide. The other thing to remember, look for the loops. If you see a lot of nested loops, you know you're potentially running into a performance issue. You're going to make exponentially more computations. Be careful about that. And last, divide and conquer when possible. We're going to talk about that specifically with trees later, but understanding how to reduce the data set you're working on can go a long way to making not only your problem solving better, like in an interview, but also making your code better in that you don't put computations on things that don't. So how does this impact React apps? How does Big O matter to React? Because we're here for Byteconf React, right? Well, it works like this. We don't need to worry about calling map, filter, and reduce a lot because, as we said, we drop coefficients. If the best way to write the code is to dot chain a couple loops, do it. It's really not that big a deal. The only time it would be a big deal is if n is very big. And if it's very big, one, you probably already know this. To be frank, you're probably working on a problem set, like maybe you're in fintech and you're handling millions of transactions a second or something like that. You would understand this. But that being said, most of the time, it's not going to be a big deal to loop through something twice in sequence. That being said, if you have to handle a lot of computations, try and get that off the rendering thread. Get that off the main thread, right? We can put that in web workers. We could push it to the server, have the server do calculations, or an API. We can tell that API to figure it out for us and just give me back the results. And we can handle this asynchronously. That way, our applications don't stop rendering. They don't stop being responsive as all these calculations are being done. So those are some good tips. And the other one kind of goes with divide and conquer, is use the right data structure for the job. This might take you some time to develop the confidence and the understanding as you learn more about computer science to really understand what the right data structure for the job is. I'm going to teach you one in the very next section, but what might be the most obvious data structure might not be the right one right away. And being open to the idea that there might be a better one could really lead to some more robust performance around your applications, and just frankly, it might even give you more legible code, more understandable code, that kind of thing. Using the right data structure can go a really long way. I'm going to take a sip of my drink. I'm feeling a little parched, so this is not an advertisement by any means. I need to get over it, but I do love this stuff. All right. So I said we're going to go through 3 things. I'm hoping to get through them pretty quickly because they can take quite a bit of time. But the first one we're going to talk about is data normalization, or as I like to call it, the art of making trade-offs. It's probably one of the first ways that I saw computer science going on in my React applications. Now, there's lots of ways we're not going to cover. I'm sorry I can't get to them all. For example, we won't be talking about like inversion of control and dependency injection, which Kenzie Dodds kind of talks about in his Simply React talk from React Rally. There's other things we could talk about, like object-oriented programming and functional programming, but there's just too much to really talk about in this talk. And I thought these 3 things I'm going to cover could be kind of useful and maybe give you some ideas of what you could do in your own applications to make some improvements to increase their performance and that kind of thing. At the very least, I hope it spurs your imagination to be thinking about new things in new ways. So, data normalization, what is it? Knowing what we know about what we talked about in Big O notation, we can realize that certain data structures might be better suited for certain tasks than others. For example, it's really easy to add an item to the beginning and the end of an array, right? We can pop or unshift or whichever one it is. I can never quite remember. But what might be harder to do with an array is to find something, right? Whereas objects, it doesn't take a lot of time for us to find things in it. Those are some of the trade-offs of those data structures. Objects take up a little more space, but arrays, they're slow. Well, if we're using lists a lot in our applications, and I'm going to assume many of you do, I mean, that's kind of the bread and butter of REST APIs, right? Even GraphQL. But in general, like getting lists of things. Maybe you're getting lists of users. Maybe you're getting lists of foods and friends or cars or other gadgets and widgets and doodads that you're using in your application, right? You're getting these lists. But if you're doing a lot of finds on them, it can be really slow if your lists are really, really long. So how can we overcome this? Well, we can overcome it by turning our arrays into objects. And this is what's called data normalization, right? We're going to take our array of items. We're going to take this list of objects, and we're going to turn it into an object so that we can look up those items by their ID and get them in constant runtime. And the way we do that is we can use a reduce function on the array, like that method, and we can turn it into an object. And I'm actually going to take the time right now And we're going to code this up live. We're going to do it live, right? So you saw the code there quickly on the screen. I'm going to make it for you here. We're going to make a normalize by ID function. So normalize by ID, and we will get an array. And I just realized I am not in the right file. That's why I have no syntax highlighting. There we go. We're going to take an array, and then on that array, we're going to call reduce. If you're not familiar with reduce, I encourage you to look it up on the docs. It comes with the first two arguments are really the most important arguments. It takes a function that we're going to use to accumulate our array down into a single value. And the second argument to reduce is our initial value. So the first function, that accumulating function, it also has two arguments that we really care about. We'll call it the accumulator. I'd shorten it to ACK and the current item. And then we'll figure out what we need to return. I like to take a second to go and get that second reduce argument in there, my initial accumulator. In this case, it's an empty object. Remember, we're turning an array into an object, and this empty object gets passed as the first accumulated value to our accumulating function. One tip for reduce, if you tend to forget to do this, sometimes it's good to write it a bit backwards, put that initial argument in there, but then also return your accumulated value, right? That's the key to reduce. You always have to return the next value. And in our case, it's pretty simple. We're going to take the ID and we're going to make it a key on our accumulated value. So in this case, ACK, we're going to take the current item and the ID. That becomes our key. And then we're just going to save the whole item on that ID. You could take this a bit further and you could return an all IDs array kind of thing. That can be very useful. I'll lead you to some documentation that'll show you how to do that yourself. But for what we're doing here, this is more than enough for what we're going to do. So we can now change arrays into these objects. I need an array of objects, and so I can prove it to you. So what I'm going to do is I'm going to make an array of the beings in my household. Yes, the beings. I'm going to start with me because I'm narcissistic like that. But I'm going to put an ID of 1 named Kyle. We're going to add my wife. Make sure I capitalize her name. She totally deserves it. I don't know if you've seen them. Sometimes they walk around while I'm recording. I can't fully pay attention to them, but I'm going to add my cats. Our first one is Krios. Are any of you Mass Effect fans out there? Krios is named after Thane Krios from Mass Effect 2 and 3. And then our other cat, her name is Tali, and you might recognize that as Tali Zaravast Normandy from Mass Effects 1, 2, and 3. We plan to name all our pets after Mass Effect characters. We're complete and total. What we can do, now that we have our array of beings, is I can use our normalize function to turn those beings into an object. So let's save this as beings by ID, and we'll take normalize by ID, and we'll pass in the being. And I'm going to console log this out, beings by ID. I'm going to save it. Yes, I really should purchase Sublime Text. I've used it for years. Oh well, make fun of me if you want. We're going to go to I'm going to slide over here to my terminal, and we're going to run that file so we can see that the array was turned into an object. So node demos data normalization. And nothing put out, so I must have done something wrong. Normalize by ID, beings by ID. Being array. Arrays returned, return that. This is where having the live stream would be really helpful because it would help me catch what I've done wrong. Okay, we'll go through it really quick. My normalize by ID takes an array. The array calls reduce. We have an accumulator and a current item. The current ID is made and we set it to that. We return the object. This is the object. That looks like it's correct. We have an array of beings, each with a different ID and name. Const beings by ID equals normalize by ID. Those are the same. and we've handed it an array. So that array should go in. Have I spelled this right? I have spelled this right. I put it in the wrong file. That's how. Y'all can laugh at me so bad. That's funny. Here we go. It's going to be funny that this is going to work so easily. Boom! It works. I knew I wasn't quite the fool I thought I was, but classic mistake. I hope you can appreciate that. Live coding, even when it's recorded, can be a bit of a challenge. But you can see what we did. We quickly made an object out of arrays. Now, this is a trade-off. Let me move to the next slide. What did we do? Oh, the next slide. Live coding time. It's live for me. It's taped for you. I know you get to see that. And here was kind of the code that we did. But what did we do? We traded space for time, right? We took up more space by making a big object, but we now change it from being an ON lookup. Like if I needed to do something like, before with just the beings, if I needed to find Krios, for example, he's frequently hard to find in our house. He likes to hide. I would have to do something like beings.find, and then x.name equals Krios, right? And I would have to do this, and it would have to go through every item. It would be able to stop eventually when it found it. So it's not, its worst case scenario is ON. It typically would be better than that. But with that being said, we'd still have to go through all the items. Now with that, if I happen to know Krios's ID, I can just do beings by ID and 3, and I get Krios really quickly, right? It would be nice if I could find him that quickly around the house. That's what we did. We changed our searching for an item with the ID from being an ON lookup to an O1 lookup. And that's something that can be really useful in your React application, specifically if you use Redux. You'll see on the screen I have a link here. About a year and a half ago, I wrote this article where it turns out I'd stumbled upon data normalization. I kind of understood this trade-off we were making, and I did it in an application, and I improved the performance like boatloads. It was awesome. It went from being this janky thing to this very smooth thing. It was so great. You can read the article and find out what it did. Someone even benchmarked it for me to figure it out for me, and it was a huge improvement. But it turns out what I did is actually documented in the Redux documentation. So the real lesson is read your docs. But Redux suggests taking your lists and turning them into objects to speed up lookup and to retrieve them from state. So look at that. It's happening in React all over the place. You got to have your eyes open to see it. I'm checking the time, making sure I'm going fast enough. All right. We got to move on. We got to move on to the next thing. I got to make sure I get through them all. The next one is memoization. And no, that's not a typo. I did not mean memorization. I mean memoization. Although it's kind of the same thing because we're going to use memory in our memoization. If I were to rename memoization, I might call it something like cachifying or something like that. What it means, it's really simpler than the name might suggest. Memoization is the use of a cache inside of a function to store previously calculated results for retrieval. We're going to trade space for time again. This time, we're going to take up some space in our cache, but we're going to save the time of not having to do complex computations again. Now, the example I'm going to give to you is a bit trivial. It's not a complex computation, but if you ever have any functions in your app that can take a long time to figure out and solve, like literally they just take a lot of processing power, but you need to run them again and again and again, it might be worth it to use this technique that I'm about to teach you in order to make that trade-off. What's going to happen is we get the arguments from our function. And if they're the same arguments as another time we've calculated it, we can just get that from the cache. We don't need to calculate it again. It's a great trade-off to be able to make. So here's the code very, very briefly. We're going to type it up here in a second because I really want to walk through the code with you as I do it. You can also see in the slides, like, this is how it's going to work. Here's the algorithm. Memo, or memoize as I'll probably call it, will accept a function as an argument. It's going to return a new function because it's a higher order function. Those of you who understand and know what that term is. It's a higher order function that's going to accept any number of arguments because we needed to be able to accept the number of arguments from the previous function, right? It's the simplest way for us to write it. we're gonna stringify those arguments so that we can use them as keys in an object. If you didn't know that, object keys are strings in JavaScript. So that's why you can use bracket notation and use strings and that kind of thing. And if the result is in the cache, I want you to return it. Otherwise, I need you to calculate it, cache it, and then return it, right? That's how our memoize function is going to work. Some caveats that you have to know before we start coding this up. Memoizing requires the use of pure function. If you don't know the difference between pure and impure, I'm going to give it to you really briefly. A pure function is any function who derives its output solely from its input and creates no side effect. What that means is side effects are like changes elsewhere in the system or state. A pure function means that when you give it the same inputs, you always get the same outputs. An impure function might change state somewhere else or give you different outputs for the same inputs. You can't memoize something like that, right? If the inputs are the same but I get different results, what's going to happen is the cache will get those same inputs and think, oh, I already have this answer, and give it to you, and it's going to be incorrect, right? Because you were expecting a different result. Maybe it came from some external state. This is why you hear a lot of talk about pure functions and how helpful they are. They're easy to test and that kind of thing, but that's a talk for another time, for another day. Just know you need to use pure functions when you're memoizing. So again, live coding time, kind of live for me, tape for you. Let's hopefully do it better this time. Let's do it in the right file. So here's our memoize file. I can see that this time. I'm paying attention. Let's make our memoize function. So memoize takes a function as an argument. And what we're going to do is we're going to start by creating a cache enclosure. So we'll make an empty object. That'll be our cache. But what we're going to return is a function back to you. We're going to return a function. It's going to operate and look exactly the same as the function you gave us. But in this case, like now there's a cache attached to it. It's just held in closure. If you don't know what closure is, there's plenty of good resources about it. I encourage you to go look that up and really understand it. So we need to return that function. I'm going to use an arrow function, and I'm going to use the rest operator to gather all the arguments that you give our memoized function. Remember, the function we're giving back is the memoized one. And what we're going to do is we first need to take the arguments and we need to make them in such a way that we can use it as a key in an object. In this case, we'll stringify them. So I'm going to call them stringified arguments. There might be a better name, but this works for me. And we'll take those args. They're an array now, right? Because we're using the rest operator that turns it into an array. And we'll call join, and we'll join it with a space. With nothing. So it just turned them all into an exact string. Now, we want to early return if that string is a key in our cache, and the results have already been calculated from a previous run of the function. So we'll take our cache, and we're going to look up stringified args. If it exists, I want you to return that result. For the sake of this example and showing you that it works in the terminal later, I'm going to console log it out first. So we'll say from cache, and we'll just get that value, and then we need to return it because that's what we expect to do. All right, assuming we haven't had the fortune of it being in cache, we need to calculate the result, store it in the cache, and then return it. So let's calculate it. We'll call it result equals, we'll take our original function, and this time we're going to spread the arguments into our original function. From there, we got our result. We need to take our cache, and we'll take our stringified args, because they should be the same still, and we're going to cache that result. All right. And now from here, I'm going to console log our result to us, and I'm going to return the result, because that's what we would need our function to do, right? Now, to test this, you would typically use memoize, I said, on a function that does a lot of complex calculations so that you don't have to run all those calculations again. You get it from cache. That's a trade-off you're making. In our case, I'm going to make a really simple function so that it's easy to see. We're just going to make an add function. So Add will take an x and a y and returns x plus y. But we want to memoize this, so every time the same two arguments get passed in, we get it back from cache, right? So we'll call it memoadd equals memoize, and we just give it the add function. We give it the add function, we get a function back. So let's use memoadd. I'm gonna scroll down a little bit so this is up in the screen for you. All right, we're gonna call memoadd on, we'll call it a 1 and 2 first, and we'll expect 3 to print out on our console. I'm also going to call it on 2 and 1 to prove the point that because of the way we stringified our arguments, we get the same result, but it'll have to calculate it both times. It won't see 1 and 2 as the same as 2 and 1. So what I'm trying to prove is that memoization might not be perfect for all your functions. You really want to use it on functions that you can guarantee like the order of things going in and that they'll be the same. Plus, stringification, like I did, is a really rudimentary way of doing it. There are probably more complex and robust ways of doing it. I would suggest looking that up as like further reading and exploration after. But we've called it twice. We haven't returned from cache yet. Let's call it again on 1 and 2. And what we should see is from cache and a 3, if I could type. Let's hope that I did this right. So we're going to go to our terminal, and I'm going to call it in the right file this time, memoization. And it worked. Boom. So you see the first line we call memoadd 1 and 2. We get that 3. Same thing happens at 2 and 1. They're storing these two objects as, maybe what I can do is I will console log the cache each time. I'm going to run it again just so you can see the cache and see what happened. So let's call it again. Oh, did I not? I didn't save. Silly me. Save now. Let's console log that cache. I'm going to clear this so it's up further in the screen. But okay, we can see that we created a key of 12 from the arguments 1 and 2, and we get 3. And then the cache got added later, and we were able to get from the cache. You can kind of see now how that process works in memoization. So how might we use this in React? Because that's a key, right? We need to bring all these computer science ideas back to React. Well, if you're using reselect and redux, you're already using it. This is kind of the same as my third point here, so I'm going to cover it in one. When you can calculate your state and memoize the arguments that went into calculating your state, you don't have to recalculate the whole thing if you've already calculated it before. Reselect does some memoization and figures out, oh, I already had this state, let me just hand it back to you, and it speeds up your application. Same thing can happen in other places in your app. You don't need to use something like reselect. You could pull the state out of your components into something like a state machine or something like that, and you can use memoization to return states quickly. It's a really exciting way to increase the performance of your application. And this can happen on like any pure function. I've had some experiments with doing this with stateless functional components. It's just for fun. It's not something I've really used in a production application, but because they're pure functions, you totally can do it. What if instead of receiving props or context and calculating what the next bit of virtual DOM should be, what if I sped that up, maybe on something that gets used again and again and again and again, I sped that up by saying, hey, I already have this figured out for you. Here it is from you can probably already begin to imagine all sorts of places that you run calculations that you can make this trade-off. Now, is it worth it? I don't know. You'll need to do some benchmarks, but you might find certain places in your application that can really be sped up through the use of memoization. I'm going to take another sip of water before we get into our last final point, and that is trees. I'm also checking the time because I got to go quick. I got to make sure I get this under the time limit. So, trees, the bane of JS interviews and why React works so damn well. What is a tree? Tree is a graph data structure comprised of nodes with any number of children and no cycles. That was perfect explanation, right? No, because you're probably like, what's a graph? What are nodes? What's a cycle? Well, A graph. A graph is a data structure made up of nodes, and these nodes are connected to each other by what are called edges. Edges can be directional. They can go in multiple directions between two nodes. A cycle is whenever several nodes all point to one another and create a loop. A tree, therefore, is a graph, but this graph happens to be a particular shape. It happens to have a parent, and that parent has children nodes, and children nodes can have children nodes, can have children nodes, but none of those childs point to each other or back to a parent. There's no cycles involved. So, like a graph structure might look like this. We have three nodes, we have an A, B, and a C, and we have four edges, right? We have the edge AC, we have the edge BA, we have the edge BC, and the edge CB, right? I felt like a bit of a gangster there making symbols, but the point being, the point being that this is a particularly interesting data structure. It's actually really useful for doing like searches and finds and that kind of thing and related ideas. But a tree just happens to have one direction and there's no cycles. This is not a particular type of tree. You can see it has several nodes, and all those nodes are either a parent or a child. The ones in the end that have no children, those are often called leaf nodes. There's all sorts of different graph data structures. I don't have time to get into them, and I hope you'll be inspired to maybe go and look up a little bit more about them today. But I want to talk about specifically trees. What if I told you you deal with trees all the time? You really do. You're dealing with them constantly. And what you're doing is you're dealing with them with the DOM and VDOM. They're trees. Have you ever heard of it called the DOM tree, right? Every website in the world is a tree data structure. I have an asterisk there because I haven't seen every website. Maybe you have. I haven't seen them all, so I can't guarantee it, but I'm pretty sure, pretty certain that they're all tree data structures, right? Well, how do we know this? Well, if we look at the markup of an HTML page, you can kind of see the tree. It's kind of upside down and inverted, but it's there. We have an HTML, that's the root of our tree. It has two children. It has a head and a body tag. Those children have children. The head has the title child, the body has the paragraph child, and the paragraph child has the strong child, right? The strong ends up being our leaf node in that branch, right? Well, if we were to make this a JavaScript data structure, a tree, it might look something like this. We have an object that has a value and a children property, and that children continues to have nodes that have value and children properties all the way down. And if you ever wrote React before you had JSX, well, you were creating trees all the time. I mean, even with JSX, you're creating trees, but it really reflects that tree data structure here. You have a create element call for HTML, the children underneath it are head, body, etc. You're using trees all the time, and if you're using them all the time, it might be time to learn a little bit about them. So we're going to go into live coding time again. I'm going to code up the node class and the tree class, and then I'm also going to code up something that allows us to test whether two trees are the same. And we don't even have to check if the whole tree is the same. We'll write a recursive function that checks if two nodes are the same and goes down through our trees. And then I'll talk about how that works in the case of React. So let's switch over to our editor. I'm going to go to our tree. I want to show you, I have this test file for trees, and you can see that it creates nodes and children and some trees and stuff like that. I encourage you to go look this up. I'll make the repo available to all of you, and I'll post it in the chat, and hopefully I've already done so. But let's make our classes. Our first class is a node class. The constructor receives a value, and that value is stored as this.value. And then any node can have children, this.children, and we'll make it an empty array. And what we're going to care about is we're going to care about adding children. I'll also have a remove child method. It's not so important for the example I'm going to show you, but we do need to be able to add children. So we get a value, and we're going to create a node from this. We're going to call it in itself, remember, because nodes are, it's nodes that point to other nodes. And we'll give that value, and then we'll push it into this.children, and we're going to return that node. This way I can return the node to my program and I can save that value, and I can call add child on the nodes. That way I can create the trees I need to create. And we'll quickly write up the remove child value. I hope that's what I called it. We don't need a value, actually. We need an index, because that's the way I'm going to look it up. It's rudimentary for now. There are certainly better and better ways to write trees, and you can probably find them in a multitude of places on GitHub. But in this case, we'll just take this.children and we'll splice at the index, and we'll remove one item. And that's all our node class. Our tree class then becomes really, really simple. Our tree class becomes a class of tree, and we have a constructor, and we get a value, just like our nodes, but this time this dot root equals new node of our value. And that's really all our trees come down to. I do need to export these, and we will export the node and the tree. And I showed you I have those tests. I'm going to run them really quick. There should be a failure on our identical nodes, but I just want to prove that the other parts of it ran correctly. It's taken a while because I have all these things running on my machine at the moment. Okay, one failed, one sweep failed, 5 tests failed. That's fine. It's all the are identical, but we should have seen tree passed and node passed. So one thing I kind of want to talk about really quick, I'm going to jump back to the slides, is that, and we'll finish up our live coding in a second, but certain trees have different ways of traversing through them. Specifically, binary trees are trees that can only have 2 children for each node, and they're typically called a left and a right. Binary search trees are a specific type of binary tree where things are sorted in a particular direction. Typically, like things on the left are less or equal than things on the right. And that allows us to make certain assumptions about the data structure. But with a binary tree, we can make the assumptions that each node might have a left or a right. And we have different ways of traversing those things. In this case, like the in order way of traversing, it's called in order, we'll visit the left tree root, then this, not the tree root, the left node, and then our root, and then the right, and it will work its way through it that way. We can also have pre-order, which will visit our current node and then the children, and then you can have post-order, which visits our children and then our current node. And visit just means it's a function that you would give it to do something at that node. You can hand it whatever function you want it to be. We could give it a print function, for example, and we could print out all our nodes, right? What we want to do is we kind of want to create a pre-order traversal of our tree. And the reason we want to do that, right, is the way React kind of does DOM diffing is you have one tree on one hand, and then it gets the next state, the next set of props, and it virtually creates the next tree. And what we want to do, and what we can do, is we can determine if these trees are the same. If they're the same, we don't actually have to do anything. We can throw that away and we can keep this. We don't waste the time on renders and figuring things out. But if they're different, we need to make updates. And this is how React's DOM diffing works. Or at least it did. I'm not an expert on fiber or any means and what's changed, and there's certainly talks about that already. But if we can figure out where in those branches that they differ, then what we can do is we can smartly update there. We don't need to re-render the entire tree. That could be very expensive in a big application. But we can render where that part of the branches start to work. And we could do this through some kind of visit function. But all I want to make for the sake of this is I just want to show you a way to make are these 2 nodes identical, because I want to show you recursively working through a tree, and we'll look at the test and I'll show you what trees I've created and why the test passed. That'll be the easiest way for you to see it. So let's make that function are identical nodes, and we need 2 nodes, node 1 and node 2. And what are the first things we can check in our nodes? What are assumptions we can make? Well, we can make the assumption that if the values are different, we can return false right away. And we can make the assumption if the children are different length, we can return them right away, right? So if, I'm going to split this onto a couple lines, it'll be easy. Value does not equal node to value. And if you're curious what font I'm using dank mono, and it's got ligatures, and that's why it's so dank and sweet. Just wanted to get that out. All right, if the values aren't the same, we can return false. Let's write that, return false. And if the children are different length, we also can return false. Length does not equal node to children. So we can return false on those occasions. If the values are the same and the children are the same length, then we need to work through each of the children to see if they met. So what we can do is we can actually use the every method. So in this case, we'll do node1.children.every. So we'll check everything in the first node against everything in the second. So child, I actually need two arguments here. I need the index. And what I want to return here is we're going to recursively call our identical nodes on the child node and then node to children. I know it's cutting off on the screen. Let me scroll that up. Sorry about that. And the index that we're at. So the first child will compare to the first child of the other tree, or the other node in this case. And we'll save that. Prettier does its thing. And we will copy paste this in our exports. And so you can kind of see what this is doing. It's doing a quick check and returning it. And every requires that each child, like each item passes the test we're giving it. Well, in our case, if they're all identical, return true. Eventually you'll return true. Otherwise, also to note, if every runs on an empty list, like there's no children, it returns true. That's why this will work. So what we can do, I want to look at the test. I don't want to create a whole new tree. I'm running out of time. I know I am, but our identical nodes, you can see some of this here. So our identical nodes, we create two trees here with the values foo. Those are the same. If they're just roots and they have the same value, we know they're the same. Same value, same children. We have two trees here that both have foo, and they both get one child each of bar. It checked those. It's going to show that it's true. Same value, same children length, different values. So here I have bar and baz. This will come back as false, right? The values on those nodes are different. Same value, different children length. We're going to get that immediate return out of that. We call two children on our first tree and only one child on our tree 2. And then on our grandchild level, I want to go all the way deeper. I want to show that that'll work. We're going to add, both of them will get one child of bar. So we're equal up to two lengths. I'm forgetting what they're called, 2 levels. And then we're going to give it the same third child. So we can go into grandchildren even, and this will recursively work its way down. Maybe just for fun, what we can do is, what can we do? If we get to here, we can do console log node 1 value, node 2 value. And you can just kind of see all the times it runs. It might be interesting in our tests. So I'm going to run our tests one more time. I'm just realizing they're getting covered up by my face. Sorry about that. Give me a second. Yeah, move this up. That's better. You should be able to see this now. We're going to run our test. It'll log out a bunch of trees. But more importantly, all our tests should pass. And it does. And we can see all these places where they're different, where they're the same, and all our tests pass. Trees really aren't that scary. They're just, they're a data structure that you can use recursion on, and they're really interesting to go learn about. So I hope you'll take some time and go do that. So I need to wrap this up. I know I'm running out of time. How might this help us in React? Well, it helps us in debugging. Dan Abramov has a tweet out there. I hope one of you can find it, or maybe I can find it by Friday. I remember seeing this, but if we can cut off parts of our code and treat our code as a giant tree, because it is like Webpack and Parcel and all these treat our whole code as a tree and figure out, that's why it's called tree shaking, right? If we can cut off parts of our tree, we understand we can eliminate the problem. It becomes a log n problem to figure out where our bugs are and figure out the answer. We can also use this to optimize renders. We can focus on bringing the state change closer to the node in which that changes. That way we don't need to implement should component update so much or re-render a whole tree when we're just changing one thing lower down. I think it also can give you confidence in using recursive functions on React elements. Maybe you're using react.children.map, that method, or something like that to do some extra functionality, and learning how to handle tree structures will help you handle those recursive function cases. And lastly, I think another way you can use this is very similar to the other one, is compound components. Ryan Florence has a talk about these. These are components that kind of relate and work together, and the only way they really work together is that the parent component has a way of figuring out what the children need. It also uses tree structure and recursive functions. So these are all over the place. They're right beneath the surface, right? They're right beneath the surface. Hope you got a little chuckle from that, just like I did. Now, I want to give you a few takeaways. The big thing I'm hoping that you take away from this, it's not even the knowledge I just tried to impart. I hope you learned it. I hope I taught it well, but mostly I hope you're inspired a bit to realize that you too, no matter where you are in your career, and especially if you're somewhere early in your career and this seems really intimidating, it's not. You can get into this. You can start to figure this out. You just have to have the patience and the persistence to wrap your head around these things. When you can learn to take big, hard problems and break them down, divide and conquer, you can start to really understand some of these really awesome concepts that are just simmering beneath the surface of what we're working on, and make the things we use so awesome and functional, right? That's one thing I want you to take away. The other one, I'm hoping it inspires you to go and learn further, or to develop these techniques and start using them in your own code. You'll find all sorts of little wonderful gifts that people have done the research and studies for years and years ago and figured out all the best ways to do these things, right? They already figured it out. So why not learn from them? Why not build upon the foundations they set? Stand on the shoulders of giants, right? So I do want to give you some resources to take away that you can use to get better at this. The first one I mentioned earlier, the Big O cheat sheet. Go check it out. It's going to help you out. Another resource that really helped me when I first started to do this, when I was getting my butt kicked in interviews, is my good buddy Brian Holt. He has 2 courses. They're on front-end masters, but you can read the docs of it for free off his GitHub repos. You have 4 semesters of computer science in 6 hours, parts 1 and parts 2. Check it out. Definitely a resource worth using. The last one, I should have brought my book into this room to show you, but the Cracking the Coding interview I actually think is really good for teaching you computer science if you didn't get a chance to learn it in school. And the reason why, because it's just testing you so much on it. It's a giant book, that giant green book, but it's written in Java. If you take the time to convert it to JavaScript, you'll learn a lot. You really will. You'll feel really confident about your skills, and it is really great prep for interviews. So best of luck with all of that. I do want to say again, thank you. I want to thank Byteconf for putting this together. Thank Christian for coming up with this idea and getting it going. And I want to thank each and every one of you for listening and putting up with me for the last 50 minutes or so. I don't have a watch. I can't tell. If you want to find me, if you have questions for me and the chat is done and you've moved on with your lives, you can always reach out to me on Twitter. I'm happy to do my best to help you. I can't always help, but I'm happy to do my best. You can find my videos on Egghead. Please go watch them. No shameless plug there whatsoever. I hope you'll come visit me in the fall on Twitch when I get my stream back up and running. I love doing like my side projects and just chatting and hanging out with all of you and getting to know you. I'm starting a newsletter as well to give you updates on things like blog posts I'm working on, chapters. I'm starting a book. I don't want to make any guarantees of it, but I'm starting one. and other things, maybe products I come up with, that kind of thing. So you can sign up for my newsletter. And lastly, if you're really just interested in finding this code or any other code I've written, you can find me on GitHub. So check out the links and have a wonderful Byteconf. I'll catch y'all later. Thank you.